AP Chemistry, this is the answers video for the thermochemistry test review, and the test will be on Friday, January the 12th. So let's go do this. All right, so there's going to be 4 basic sections, not necessarily in this order, doesn't matter what order. So enthalpy of formation, again, enthalpy of formation is the enthalpy, that is the heat going into or out of a chemical reaction when you manufacture a compound like one of these out of its most basic elements in their most stable form. So oxygen would be O2, not O. We talked about this in class. And it's making 1 mole of that. So what you can do is use these. Now, we can use the enthalpy of formation of sodium hydroxide, of hydrochloric acid, of sodium chloride, and of water, and use those to figure out the enthalpy of this overall reaction by taking the enthalpies of formation. Okay, you don't need to understand it any deeper than that. It just happens to work. Now, if these had coefficients in front of them, you would have to multiply whatever number you get up here by the coefficient, but these happen to be 1. Now, since I did this one in class, let me do the one down below. So this is the combustion of methane. All right, and so the formula is the sum of the products minus the sum of the reactants. Reactants are on the left, products are on the right. And this N simply means you multiply by the number of moles. So when we get the number for water, H2O, we're going to have to multiply that by 2, okay? So again, you can easily get confused, so just remember that these go over on this side, and these go over on this side. They crisscross in effect. Okay, so let's get going. So carbon dioxide, try to get the whole thing on the page. I don't know if that's going to be possible. I'll do the best I can. Carbon dioxide is right here, and it's negative 393.5. It's on the product side, so we're going to put it over on this side. And there's 1 molecule of it, or 1 mole of it. So we're going to do this. I'm going to use square brackets as a set of parentheses. Let me get this up here. I'm just going to have to move the camera back and forth. So it's 1 times, I'm not going to write the 1, 1 times negative 393.5. Now you're going to add these together. Plus parentheses. So I use the parentheses because you might have a plus negative. In fact, you usually will. And that is for water. Okay? And I'm just going to erase this because there's 2 moles of water. So I'm going to put 2 times, and in parentheses, we come up here water. We're assuming it's gas because that's the number we have. Negative 241. It says, in fact, it says liquid, but forget that. Let's just change it. Let's make that gas, okay? All right, make that gas. Okay, 240. I don't want to get into that. It's a detail that we don't need to deal with here. Okay, there we go. So again, be sure you understand that this is for carbon dioxide. It's up here. It's 395, negative 395.5. This is for water, is that number, and you have 2 moles of it right there, so that's how you do it. So you're going to add those 2 numbers together. Now you're going to put a minus sign. You're going to subtract the reactants. So another big square bracket. The reactants are CH4. So we got to come up here to the top, and that's negative 74.8. In other words, that's what it takes to put a carbon and 4 hydrogens together to make CH4. You'll have 74.8 kilomoles per joule of heat coming out of that reaction. That's what that enthalpy of formation means, to make 1 mole of CH4. Okay, so you have, it says, the equation says you have 1 mole of it there, so it's negative 78.4. Okay, and we're going to add that to O2. Now, O2 does not appear on here. Pure elements, such as oxygen, have 0 enthalpy of formation. Okay, so remember that. N2 would have 0, H2 would have 0, so O2 has 0, but I'm still going to put it down here. It's 0. And we're going to close that. So now we're going to do the math, and we're going to take negative 395 plus 2 times negative 241. Okay, and I'll pause the camera for a sec. Okay, and what I get here is a negative 877.1, and then I'm going to subtract from that negative 78.4. Okay, so remember, negative is going to mean a plus. So I'm going to do negative 877.1 plus 78.4. And that gives me 798.7. Negative 798.7 kilojoules per mole. So that much heat will come out of this chemical reaction, okay? And it's per mole of CH4. There's 1 mole. So that's how much heat you're going to get by combusting, by burning CH4, okay? And that's the final answer that you're looking for. All right, so again, the strategy is products on this side. You add the two products together, and reactants over on the right side, you add them together, and then you put them in square brackets. You put a minus sign between them and subtract, okay? All right. All right, number 1 we did in class already. I'm going to skip past that. Okay, we answered all the questions. We answered all of these. I'm going to say them very quickly, though. Okay, thermochemistry is the study of heat coming in and out of a chemical reaction as a way of knowing the energy of that chemical reaction, how much energy is in the bonds. Okay, explain the meaning of system, surroundings, and universe. The system is what you're studying. The surroundings is what's outside of that. So in the case of our sodium hydroxide, the bonds in the sodium hydroxide, when we dissolved that a couple months ago, that was the system. The surroundings was the water and the dissolved sodium hydroxide, which receives the heat. And the universe is simply the two of them together. Okay? What are the two kinds of energy involved in a chemical reaction? That would be work energy and heat energy. So that would be this. So change in overall energy equals change in work plus change in Q. Now, heat here is the generic form for heat. That's a Q. That's the way I make my Qs, is Q. It's not H. It's not delta H. Okay, so again, think of the car. The energy that it gives up goes out into work and into wasted heat. All right? And it's like money in your bank account. If the energy goes into the system, it's positive. If it comes out, it's negative. Same with work. Goes into the system, it's positive. Comes out, it's negative. Heat goes in, it's positive. Comes out, it's negative. What is the definition of heat? Heat is the transfer of thermal energy between two objects at different temperatures. Now, one of those objects could be the atmosphere. So when you boil a pan of water on the stove, the heat comes out of the pan and into the atmosphere. So the pan of water is hotter than the atmosphere, so it's transferred from the hotter pan of water to the cooler atmosphere. Okay, so that's the second object. So two things have to be at different temperatures. What is the definition of work? Work is force times distance, and the abbreviation is W. Okay, so it's force times distance. Okay, which of the two, work or heat, do we focus on in chemistry? We're interested in heat because work kind of complicates things. Physics is more interested in things moving and work, but chemistry wants to just study the energy in chemical bonds. And if the energy equals the work plus the heat, as we set up in number 6, but we can get rid of the work somehow and make something not move, then all the energy will come out in the form of heat. So if we can measure the heat somehow, determine the heat, we'll know how much energy was in those chemical bonds. So we're interested in heat in chemistry. Define change in enthalpy. It is the heat going into or coming out of a chemical reaction. So it's a very specific kind of heat. And it's delta H. Delta, triangle, H. What is the abbreviation for change in enthalpy? I'll go ahead and write that one down. It's delta H. Okay? When is enthalpy positive and negative? So when heat is going into a reaction, that would be an endothermic reaction, then enthalpy is positive. Just like money into your bank account is positive. When heat comes out, like money out of your bank account, then that's exothermic, and that's negative delta H. All right. Using the example of the car, explain the relationship between energy, heat, and work. So the energy is the gasoline, and all that gasoline eventually gets burned and does two things. It creates work. It makes the car move forward. That's what you want. But most of it actually comes off as wasted heat into the atmosphere. So all of the gasoline energy goes into either heat or work. That's the delta E equals delta W plus delta Q. Okay, what is the definition of temperature? Temperature is the average kinetic energy, that's wiggling energy or moving energy, of molecules or particles in a substance. So it's internal to the substance. So if you think of a solid has temperature based on how much the molecules wiggle, how much they vibrate back and forth. If it's a gas, it's how much they move around. Remember, we said temperature can be thought of as the speed of the gas molecules. So the definition of temperature is the internal kinetic energy. Kinetic energy is the energy of motion of a substance. Okay. Do the atoms in a piece of iron have any kinetic energy? Yes, they wiggle. Nothing in the universe is standing still, so they wiggle back and forth, and they do have kinetic energy. Any kind of movement is kinetic energy. 15, what are the two standard units of measure for heat? It's joules, abbreviated J, and calories, abbreviated CAL. Okay, if 1 calorie equals 4.19 joules, how many joules is 25 calories? Again, I'll just show you this one real quickly. So 25 calories, it's just a basic stoichiometry problem. You have 4.19 joules over 1 calorie. Calories cancel, and you end up with 25 times 4.19, which is about 120 or something like that, okay? Joules of energy. This one's the same thing. It just goes in the other direction. We did these both in class. Explain when heat and work are positive and negative. So again, when they're going into the system, they're positive. When they're coming out, they're negative. So again, how is this like money into or out of your bank account? So we've talked about that. Define endothermic and exothermic. Exothermic is heat coming out of the reaction. Endothermic is defined as heat going into the reaction. Okay, what is specific heat? It is a number characteristic of each substance. Each substance has its own specific heat, and it tells you how much the temperature will increase. Just think of it this way. It's how much will the temperature of that substance increase if you put in a certain amount of heat, okay? How much will the temperature increase? The other way you could think of it is if the temperature increases or the temperature decreases by a certain amount, how much heat will come out of that object. So it's a relationship between the amount of heat that will go into or come out of a substance and the change in temperature that that substance will experience, all right? So it relates heat and temperature. Okay, so now this is a bond energy problem. So we're going to do these. It's a lot of number crunching. So let's go ahead and do this. So here's a balanced chemical equation. So C3H8. Now, I gave you the Lewis dot structure. You need that because you need to know how many of each type of bond you have. So let's start with this. We have one molecule. So I'm going to put just a little table here for the first one. Molecules are moles. And this is number of bonds of each type. And this is the bond energy. Okay, so let's take the CH first. So you have one molecule of C3H8, and carbon, hydrogen, you have 1, 2, 3, 4, 5, 6, 7, 8. So it's 1 times 8 times the energy in a carbon-hydrogen bond. Now this is just an average energy. So let's look at this. So carbon-hydrogen is right there. It's got 414. And now you can multiply that and figure out how much is in carbon-hydrogen bonds. It's 8 times 414, and that's going to give you 3312. Okay? Now for oxygen, you have 5 molecules. Oh, whoops, I didn't finish. Now you've got carbon-carbon bonds, and you have 2 of those. One right there and one right there. Don't count the number of carbon atoms, it's how many bonds. So carbon-carbon is one molecule still, times 2 bonds in each molecule, times, and now we go to our sheet again to find carbon-carbon. It's right there, it's carbon-carbon is 347. Be careful, don't pick the double bond, it's the single bond carbon-carbon, 347, okay? Okay, you multiply that out and you get 694. Okay, all right, and now you can add these all up down here, 3312 plus 694, and that means the total energy in one molecule of propane there is going to be 4,006, and I'm not going to worry about units of measure. It's kilomole, it's kilojoules per mole. How many thousands of joules you get for every 6.022 times 10 to the 23 of those molecules, okay? Now we're going to go over, I'll draw a line here to keep this kind of separate. So you have 5 molecules of O2 times, and you have one O double bond. That's the only bond you have there. So we're going to come back here, and there we see an OO double bond right there. It's 498.7. So there's one of those, so I'll put that there. That's the number of bonds times 498.7, and that's going to equal 2,493.5, 2,493.5. Okay, and we're done with that. That's all we have there. Now we got to come over to this side. I'm going to get a little tight on space. We have 3 molecules times there's 2 carbon-oxygen double bonds. There's one of them. There's the other one. Okay, so there's 2 per molecule. And now you got to be careful here. You look for carbon-oxygen double bond, and you see it 2 different places, there and there. The one with the asterisk down at the bottom says this bond energy for CO2. I'll actually write that more clearly here. That's the bond energy for CO2 is the 799. So we're going to come back here and say times 799. So it's basically 6 times 799. And that's going to give us 4,794. 94, okay. And now we have water. So water, draw a little line there. We have 4 molecules of water, and each one has 2 hydrogen-oxygen single bonds. One there, one there. So times 2. And now we go over and we look for hydrogen-oxygen single bond. It's right there. It's 460 kilojoules per mole. So times 460. Okay, and we're going to multiply that. So we have 8 times 460 if you do all that. And that gives us 3680 kilojoules per mole. Okay, so I'm going to write this one. I'm just going to move it down here. So it's 2493.5. Now I'm going to add these 2 together. And what I get is 2493.5 plus 4006 gives us 6499.5. And that's a positive. Why? Because you need to put energy into the reactants to break them apart. So that's going to be a positive energy. All right? Now, over here, so I'm going to put that in my square brackets that I like to do. Over here, square brackets, we're going to have this plus this. This is the energy of these 2. So it's going to be 4794 plus 3680, and that equals 8474. That's on this side. So this is really where the arrow is. I'm kind of having to draw it because I ran out of space. So you subtract these 2. This is energy out. Okay, energy in to break the bonds apart, and then when they get put back together in products, they want to go to lower energy. That's why they do it. They're more comfortable. They're comfy at lower energy. So this is going to be negative. Okay, so it's going to be 6499.5 minus 8474, and that's going to equal negative 1974.5 kilojoules per mole. That makes this an exothermic reaction because energy is going out, and that's what you would expect. You're burning propane for heat or for fuel of some sort, and so you would expect it to be exothermic, and it is, okay? So it's a lot of number crunching. That's how you do these problems, okay? All right, let's go to this one. I did the other Hess's Law problem. I just want to verify that in class on Thursday, and I did. That was one that used enthalpies of formation. This one doesn't necessarily do that. Okay, so let's go ahead and do this one together. Okay, so what we're doing with Hess's Law is there's three things that we can do. We can multiply, and multiply might be multiplying by a fraction, like 1/2, okay? We can reverse, that means turn the reaction around. Okay, and the third thing we do at the very end is we add or subtract. If they're on the same side, two of the same compounds are on the same side, you add them, and if they're on opposite sides, you subtract them. So those are the three things we can do. All right, so again, you want to keep yourself organized, okay? I have my way of doing it, and you can have your own way. So what we're trying to do is, the purpose of this is, we want to find out what the delta H of this is, of this target reaction. We don't know what it is, so we're going to put a question mark. That's what we're trying to find. We know the changes in enthalpy of these three. Now you know what they're called. They're called elementary reactions, okay? So this has nothing to do with kinetics, but it has to do with how you use Hess's Law. So here we go. So I'm going to down here, I'm going to write equation 1a. Okay? All right. So the way you approach this problem is you go up to the target and you try to find something in the target that only appears once down here. You want to stay away from things that appear many times down here. Oxygen is the one that most commonly does that. So for example, you see an O2 there and an O2 there. Stay away from that. So let's go to N2O. So I look down here and I try to find an N2O, and there it is. It only appears in one place, and it's in equation 3. So we're going to start with that. So we see that N2O here is on the left side. The two things you want to ask is which side of the arrow is it on and what is its coefficient. So it's on the left side of the arrow and it has a coefficient of 1. So this one is on the left side of the arrow. That means we don't have to reverse the reaction, but it has a coefficient of 2. So what we're going to do is multiply this equation by 1/2 so that 1/2 times 2 becomes 1, and then you'll have 1 N2O that matches up with 1 N2O there, okay? So over here I'm just going to make a notation, times 2. That's what X2 means, times 2. So I'm going to come down here without reversing it, just come down here, multiply this by 2, and you get N2O rather. Okay, that got cut in half. And now you have an N2, you have to multiply that by 1/2. So 1/2 times 2 is N2. Plus, and now you have an O2, you have to multiply that by half. So you put 1/2 O2. This is the only place in chemistry, or one of only two places, that you have fractional coefficients. And you're okay with that. Now this is the key. You've got to take the enthalpy and cut that in half, okay? So half of 163.2. Okay. And that's going to give you 81.6, and it's a negative. You don't change the sign. Kilojoules per mole. Okay, now I'm going to put a line through this because I don't want to accidentally add this in again later on, okay? In fact, I'm going to put a line between both of these like that. Okay, now, so we've taken care of this. Now let's go to NO2. So NO2, where do we see it? Right there and nowhere else. Okay, so we look at it, and if we look at this, at the target, there's NO2 on the left side of the arrow, and here it's on the right side of the arrow, and here it's the coefficient is 1, and here it's 2. So we need to do two things to this. We need to reverse it, and we need to multiply by 1/2. So I'm going to write that over here in my notes. Reverse and times 1/2. I put times 2 here. I hope you caught that. That was wrong. It was times 1/2 for number 3. Sorry about that. Okay. All right. Okay, same thing here. All right, so let's go ahead and do that. So that means we reverse it. So that means this 2NO2 is going to come over to the left side, and you're going to cut it in half. So it's just going to be NO2. Now the arrow. Now we look at this. This goes over to the other side, and it cut it in half, so it's NO. Plus, and you cut this in half, and it's 1/2 O2. Okay, so what we have to do with this number is cut it in half and take off the negative sign. Change it to a plus sign. When you reverse, you change it from you change the sign. So it's going to be positive 56.6. Okay, I'm not going to bother with the units of measure. Okay, there you go. Positive 56.6. Okay, so now we're done with this one. All right. Well, we're not totally done with these two. You're going to see why here in just a second. Okay, now we have 3NO. Okay, so we need 3NO. So up here we have 2NO. It's on the right side, but you need it to be 3. So do you need to multiply by 3/2 to get that to be 3? No, because you have another NO down here in equation 2a. So if we take 2NO plus 1NO, we get 3NO. So what does that mean? It means we don't have to do anything to equation 1. It's already ready to go. So I'm going to go ahead and write it down here. I want to rewrite it because I don't want to use these equations anymore. So we've got N2 plus NO2. Okay, and that goes to 2NO. And that means we don't change this at all. So it's delta H equals 180.7. Boom. Okay, and I made an error when I copied equation 1. I just meant to copy it exactly, but I copied it wrong. It shouldn't be NO2 here, it's O2. So it's N2 plus O2. It should be exactly like this one right here. Gives you 2NO. Okay? So now, by the way, I want to put a line through this. So I've used all 3 of the reactions. So now, before we add up here, we want to go ahead and add everything. So we have an N2 on the left of this arrow and on the right of this arrow. So they subtract out. They're gone. Okay? What do we have over here? Let's avoid O2s for now because you got a bunch of them. We got 2NO on the right side here, plus another NO on the right side of this arrow. That equals, let me go ahead and write this out. That equals 3NO. Okay, so we've done those. I'm going to circle those because we used them. And then I've got NO2, and I don't see it anywhere else, so it goes over here. Plus, and I've used that, and now I got N2O nowhere else, so it goes here. And you see that matches up with our target. It doesn't matter which order you put N2O and NO2 in. The same thing. They're added, okay? So this matches our target. That means we got everything right. So now we add all these numbers together, and we get 180.7 plus 56.6 minus 81.6, and that gives us 155.7 kilojoules per mole. So that is our final answer. That's the enthalpy that we were looking for up here, that delta H equals question mark.